Today I am going to talk on the first lecture on two topics. One is what I call motion in short crested, basically 3D waves. This I will talk first, and later on maybe I am calling coupled motions. See, the reason I want to talk about motion in short crested wave is that so far what we talked earlier was a motion in what is called a 2D or long crested waves. Okay, we have briefly discussed earlier how we can describe a short crested wave by simply multiplying this with a spreading function and taking also the fact that waves come from all directions. Basically what we have defined that 3D spectrum S 3D omega is equal to S 2D omega, well there is a theta here, multiplied by F theta. Like that we described. In other words, if you recall, what we have done is that we said that if we assume waves are coming from all directions in addition to all frequencies in one direction, then the spectrum that we get is a bell-shaped spectrum. In other words, the spectrum that will look like is something like, coming from all direction, and it will look like this. Then you have to draw here, then you have to draw here, you have to draw here, etc. It becomes a kind of a bell-shaped graph. In other words, let me put it this way: if you have drawn this and if you rotate that this way, suppose there is a graph here, rotate that along with pulling it down, that would imply that you are actually simulating or representing an irregular waves where all the waves are coming from this direction plus this direction plus this direction plus this, etc. That means you are assuming that all the waves that are, the wave height or elevation that you are getting is because of sum of all waves coming not only from one direction of all length but also from all directions, but the directional spreading gets sort of thinned down. In other words, there will be much larger waves coming this side, little smaller this side, little smaller this side, and ultimately no waves this side, and like that. And this was simulated by kind of multiplying this with a spreading function. So in essence what we are doing is that, see, that we are saying that there are waves coming. Just give 3 example. In one case I have all the waves coming from this side and it gives some energy, but in this case I will have all the waves coming from this side, but of course it cannot have all the energy, so it will be maybe little smaller, that if this is, and then there will be some waves coming from this side, some coming from this side, like that. Now what is happening now, if this is the representation of spectrum, now if my ship is moving in such a wave, obviously I should have some mechanism to find out the response in such a wave, and this is more realistic because just think of it. A ship is moving and I am trying to find out irregular waves coming all from the, if you rather draw this way, all coming from beam waves. Now actually if all waves came from this side, then the shape would have rolled heavily. But if supposing in reality you will find that not all waves can ever come from one side, there will be quite some waves from one side, but there will be some from this side, some from this side, etc., etc. The waves are not normally all coming from one side, and if that happens, obviously it affects the response. For the clear case here, the roll, if you assumed all from one side, maybe it would roll say 30 degree, but if you assumed it is spread, then it will be probably less. Of course, from the design point of view, what we still do is that we take long crested wave, because if I have designed the shape to withstand roll for all waves coming from one side, obviously if it is spread it will be less. So we are on a safer side. That is a different issue, but we should still know how we can calculate in short crested wave. Now the idea is very simple. See, short crested wave goes like this, that the principle goes very simple, that let us say I will just draw a case of waves coming from all sides. This is a wave direction, etc. waves are coming from all sides, and for each side I have a spectrum. So I have S3D, or rather anyhow omega theta is given by S2D omega into f theta. F theta is a known function, therefore when theta equal to, for example, 0 degree, when I know that like f theta become 1, like that when theta becomes plus minus 90 degree, f theta becomes equal to 0, and in between that it goes. That means what you are multiplying the spectrum, see this is my wave direction here, what you are multiplying with that essentially is a, no, it's not 1, sorry, it will be some factor, maybe 2 pi, I forget, some factor, so that when you sum them all up, actually the area under this and area under this becomes same. The theory, let us say it is known. What I am trying to say here is that we have a representation of short crested wave, okay, when we know how much of waves are coming from direction 1 and how much is from direction 2, how much from direction 3, how much from direction 4. Let us say you break it in say 10 degree interval. So you know all the waves coming from the dominant direction, if I call that to be say 0 degree, then all the waves coming from 10 degree, 20 degree, etc., etc. Now let us say on this the ship is moving in this direction. The ship heading is like this. Obviously what would happen is that it's very simple. Now I would know now all the waves coming from this direction to it. Then in other words, I know I know how much of waves come from this direction. So now, but all the waves of this direction makes a heading of so much angle. So I would know that look, the ship, as if ship is going with so much angle in all these waves. Then next time I will say that as if the ship is going with this heading angle with all these angles, like that. In other words, what happens now, I have to, all that I have to do is I have to spread it out over the angle also. See, if you look at the principle, now response spectrum, this is response. If now let us say that I have made these changes omega e, etc. Response spectrum in omega e is RAO square into S E omega e. This is my formula. But now what is happening, my SE is 3D, which has omega e and theta in a 3D case. Okay, so this becomes, obviously I have to have RAO square, which will be omega e and theta, and this is going to be my SR omega e theta. Basically I have to have this, I have to simply add that. Now when you do that, you see what you have to do is that you have to actually do the calculation. Now this part, if you now break it further, this is RAO square omega e theta into, now this part is SE 2D omega e square into f theta square. Okay. So now what we have to do, obviously the procedure becomes somewhat simple. We have to go one by one for various angles. I will just show you what we should do.
2d square and f theta square.
Yes, yes. So because this 3D is 2D plus no, there is no square here. Sorry, the square is not there. You are very right. This is just this. This is S3D is equal to S2D omega into f theta. That is right. The square is not there. You are very correct. Just this part becomes square. So what we are doing is that we are simply actually doing the calculation repeatedly. See what would happen here, we will have this thing, say wave angle theta, okay, equal to, let us say 0 degree. You will start from that, or let us say you can start from minus, you have to do it from minus 90 to plus 90. So let me say we start from, or let me say maybe we can go this way. Theta is so and so, wave heading angle, ship heading. Now you see here, ship heading angle is a mu. Now here this is interesting. See, this is my x-axis. So my wave here is 90 degree. This is the wave, and my ship heading angle is actually this, say mu. Therefore the relative angle of that becomes actually you can say theta minus mu. So it becomes theta minus mu. Okay. So then we this will tell me what is my sort of heading angle with respect to the wave. This heading angle is absolute heading angle. This is absolute heading angle, because you are having a reference system. See again, this is my x-axis. See, I am giving the principle only. This is my x-axis. Okay. So now this is my dominant wave axis. Let us say that this is my dominant wave direction. Therefore, most waves are coming from this side. You can take any of the reference, that is always much better, because if you take this dominant, then integration will become minus 90 to plus 90, because all the waves will be between this sector. So wave is my coming from this direction, but the shape is my moving in this direction. So now I take, say, all the waves from this direction. I must find out, now all these waves from this direction implies that all the waves are making an angle of theta minus mu. Say this is equal to, say, 30 degree. So that means I am trying to find out all the waves when the shape is moving in all these waves at an heading of 60 degree. What is my response? So now this becomes equal to, say, theta minus mu equal to 60 degree. So for that, for this, now I will figure out omega E, AC omega E, which I have got, f, in fact there has to be f theta. So therefore I have AC omega E into f theta. That becomes my component for 3D part. Here I have got RAO omega E theta. Remember, theta actually is not theta. This is theta minus mu here. This is theta minus mu. That particular heading. That is that RAO. Then here the here I can say SR omega E into. I can call that theta also, doesn't matter. It's a function of that. Mu will remain constant after all. 30 degree will remain constant. So I can call it theta here. So I get this. That means what I have done is that I have found out what is my response spectrum for all the waves coming this side. Now similarly I have to repeat that for all the waves coming from this side and for all the waves coming from this side. So in other words, actually it is nothing but an algebra. We don't go through this detail, but it is nothing but an algebra of simply taking two-dimensional spectrum for various angles. Okay. So what would happen now? If I end up doing that and then add this area up, then I will again end up getting a spectrum which is spread. See, earlier I have got a spectrum which was actually in one direction. Now I get a spectrum which is also spread. See, for example,
Only RA is becoming square in case of.
no. RAO square is always there. RAO square is always there, but RAO is now has to be taken for also direction. See, we will give an example of just one wave, let us see, just for illustration. Supposing in a 2D case you assume that there was a wave coming, only one wave was coming of some height. Let us say some wave was coming of, say, height of 10 meter. In this direction, my shape was moving in this direction. So what I did, I would find out, instead of frequency I am trying to say that as if there was only one wave coming this side, 10 meter height. It will have certain energy. So I would find out if this wave, what is the shape response. That's it. But now what happened, I am trying to say that this 10 meter is energy is not all 10 meter. There is actually as if a wave coming of 5 meter here, there is a wave coming of, say, 3 meter here, there is a wave coming from 1 meter, like that. As if the wave energy is spread. No, I say that no, the wave that is coming in this direction of 10 meter, I assumed it is not so. What is happening is that there is a total energy of so much equivalent to a 10 meter high wave, but the direction of the wave is spread. That means that energy is spread due to a wave of 5 meter height this side, due to another wave of 3 meter height this side, due to another wave of 1 meter height this side, etc. So that when you sum them together, the energy becomes same as the energy of a wave coming in 1 meter. Now if you see that, now the shape is moving in this direction. Now what I have to do? This 5 meter wave gives a response to that. This 3 meter wave gives a response to that. This 1 meter wave gives a response to that. But they are different because this 5 meter wave gives a response because of this angle, whereas this gives because of this angle, etc., etc. Simple case. Supposing there is a ship moving in a beam wave, let us see. Suppose the ship was moving in this direction and all the waves were coming this side. You have got a very large roll, but instead of that, if you assume that there is a small wave coming, another wave coming, another wave coming, you will have a less roll angle. Conversely, supposing another thing also, suppose all the waves are coming from this direction, you have no roll angle. But if you assume that no, some waves are coming from this, some waves are coming from this, etc., then you have some roll angle. So what happens is that when you assume that the waves are not from one side but from all sides coming, then you have got different kind of response. It is normally mellowed down, like it is spread. So this is what is how we can find out motion in three-dimensional spectrum. It is turned out that most motions in three-dimensional spectrum would be lower than corresponding maximum you might get in one side. For example, say pitch. If the ship is moving in these waves, it may have a large pitch, much large pitch. But if you assume the waves are coming from all sides, then it will be less pitch. So normally what happens, the maximum you get from two-dimensional spectrum is always more than what you get from three-dimensional spectrum. A typical example I show you here. What would happen? See, for example, if you say heading angle here, some angle, ship angle here, long crested waves in 90 degree, you will find out that the roll motion is very small here, 0 degree, very small 180 degree, but it is very high like that, isn't it? See, if you take short crested sea, long crested sea, waves are all one direction. If waves are coming all direction to which ship makes 0 degree, that is following or head, no roll. There also no roll. Beam, there is much larger roll. You understand? This is roll. See, if you assume all the waves were coming in one direction, and if they are all coming from the 0 degree, that means the shape is like that, the waves are all coming like this. What is the roll? No roll. I mean, this is all irregular waves coming, roll is 0. If it is coming from this side, roll is 0. If it is coming from this side, roll is very high. But now if you assume that, look, although my dominant direction is this, my waves are actually spread over. If I take a short crested assumption, then although it is 0, but there will be some roll here, and when it is 90 degree also, there will be maximum but less than this, so the roll curve will look something like that if you take a short crested spectrum. What is this angle? This angle is normally defined as the dominant angle of the dominant wave direction. In other words, in case 1, all the waves was in that direction only. In case 2, most of the waves in that direction, but there are quite some waves also from other directions spread around that direction. So even though that direction of wave do not give roll at 0 degree, because there are other waves from other direction, it will give you some roll. On the other hand, if there is it gets maximum roll because of all the waves in 90 degree, but now here it is not all the so much waves on 90 degree, they are spread, so it will be less, so it will look more spread. Say pitch, for example, if you see the pitch here again, in say this is 90, this is 0, this is 180. If you see pitch, you will find that the pitch, like at 90 degree, it doesn't pitch. So the graph will look something like that, and again something like that. Because at 90 degree, when the waves are coming this side, the shape does not pitch. See, when the waves are coming beam, see, waves are coming this direction, the shape doesn't pitch, isn't it? When it is coming this side or that side, it pitches maximum. So it is maximum like that. But now if you take a three-dimensional spectrum, you will find that this is actually will come down more spread. Actually, the drastic difference that comes in roll. But as you can see, if you want to do a conservative design, this is maximum. Again, this is maximum. I mean, this is higher. So therefore, therefore what happens in a design, what you can do is that if you have designed a ship which survive at long crested waves, then you are actually designing it for a worse condition. You are on a more conservative side. But some people will say, see, it's a debate will go on, because although suppose you are doing and you say that the ship is basically surviving so and so, but your prediction will show that the ship might have maximum roll of say 25 degree or 20 degree. But then the designer would like to convince the owner that, look, actually it is less than that, 15 degree only. So they want to insist on doing maybe 3D spectrum. What I am trying to say is that if you have designed it to survive for a long crested sea, 3D spectrum will always be lower normally. So from a design point of view, if it is good for long crested wave, it will be good for short crested waves. Short crested waves are more difficult to calculate, more complicated, it looks different. However, the procedure for calculation is simply basically repeating the long crested wave number of times. See, long crested you have one table. Here you have to have, say, a table for various angles. That's all. Like it is the difference between hydrostatic and cross curves, where one you do for one angle, another you do for all angles, and add them up. So when you try to find the area also, you have area under each angle, then add them up over area. You see, you want to find out area. So I have got area here is 3d r omega e theta, d theta d mu, the two angle. So you will do in two phase. You will do, actually this is written now at RAO square omega e into say theta, something like that, into here you have got s e omega e and again f theta. So you have this part taken as d omega and this part taken as d theta, and you separately multiply. So it is actually, it is simple. What I am trying to say, it will become very I mean you do in two fashion, because it may not be like this. You can do that first this one and then this one. So it's a very simple thing. You see, you are doing it for one angle, theta equal to 0 degree, then you are doing for theta equal to 90 degree, then you are doing for theta equal to 180 degree. You find these areas here, you again integrate them along the theta angle, you get a total value. That's all. So the conceptual difficulty is very straight. You will actually learn that this kind of thing always when you really do a problem. Otherwise, in the classroom we cannot see the numbers. So my purpose of telling you in the classroom is that it is not complicated, it is simple algebra. In fact, it is absolutely pure and simple algebra. That is all. Just you have to keep your head, and all that we need to know is to just keep that in mind, that in the short crested sea, all we are saying is that all the waves are coming from various directions. So for each direction I must find out what is the shape response and again add them up. So the wave is broken in earlier case, various waves coming from one direction, but now we have to spread that also various direction, and the spreading is also well defined. How much it is spread from other direction, the energy is very well defined, that if all the waves are coming from this direction is of unit 1, then direction 2 will be that into some function of theta, because we know that if the waves are coming from, if the wind is blowing this direction, so if the wind blows this direction, most of the waves will be in this direction, no waves will come from the opposite direction, and as you go to 90 degree it will be 0. So when the wind is blowing in one direction, you will expect most waves are this direction, but it will be spread. That's why up to 90 degree it is taken. The logic is very simple. Okay, so we will not be doing problems of that, but I wanted to just tell you about the short crest wave. As I said, the full procedure for response in irregular waves is a algebraic process. Pure algebraic process. Some people call it actually in offshore industry post-processing, not even processing, because there is nothing. It is the RAO getting where the hydrodynamic comes in. The other part is simply break it, like it's like 100 is broken into 5 plus 5 plus 3 plus 2 plus 1, and again add them up. It is stable. So that's what I keep on insisting in the class, that this part is a more simple part. Although the first paper that came out gave this idea of how to find out motion in irregular waves. This paper was called Determination of Ship Motion in a Confused Sea. Okay, it's a very famous paper sent by SDRs in 1953. But I keep telling that there is nothing confusing about confused sea. It is the most straightforward thing. It is just algebra, pure algebra. And now tomorrow, say somebody wants to find out bending moment, not heave. All you do is to take RAO for bending moment. That's all. So you want to find out midship bending moment in irregular waves. Okay, so you find out bending moment for regular wave 1, 2, 3, 4, 5. Add them up. Same way, bending moment divided by per wave amplitude. That is the RAO. Any response amplitude by the input wave is a response amplitude operator. You want to find pressure, fine, you take pressure at any point, divide by amplitude. So anything that you want to do, it's a pure and simple algebra. Okay, there is just nothing to it. So I want that. And then 2D is a more simpler algebra, 3D is little more one step ahead algebra, because you have to add also the directional component. So we call it short crest. Saying that, also I am trying to tell that normally, even I repeating this, that in any design, if you have not done 3D, never mind, because if you have designed the ship which is good in 2D for all direction, it will be definitely even better in 3D. Okay, because if it is suppose maximum pitch when it is head C is say 5 degree, in a short crested 5 degree will be 4 degree. So you don't worry, the shape is surviving 5 degree, fine. So this is what we need to know. This is pure algebra, as I said, some people call post processing. Okay. We will be doing some problems, perhaps very simple problems, because what happens is sometime is that you remember that unit becomes important. See, when I do, I again just mention this little bit, omega into f theta. This way the integration comes in. This is d omega, this d theta. You see this area, I mean when you do s omega theta, d omega d theta, this is written as 2d omega d omega and 2 like that. Now what happened? You see that the units are same because integration over d theta do not contribute to unit. D theta is radian, which has no unit, therefore the unit is still meter square second. This unit also remains meter square second because this is meter square second, this is no unit. So it is unit is still meter square second for the wave part, and for the response part it will be response, the unit of the response square into second. So it will, there is no contradiction whatsoever when you do over the angle, because angle does not have any unit. Okay, so that also should be remembered very clearly. Okay, this is very briefly. In fact, one problem that will occur, that numerical complication that will occur is that if you do a spreading, see supposing, here I want to tell you this very briefly, supposing there is a ship going this way and I was trying to do all the waves coming from say this side. So I have done the calculation all, but if I want to do now spreading a 3D, then I have to consider all the waves coming from up to this direction to this direction. So there will be some waves that will be following. Although the primary wave is maybe at 85 degree, there will be some wave which is coming at 175 degree. Then in the following waves you may encounter having all funny looking transformation, all this type. So you have to be careful in algebra, that's all. Even though the dominant wave is head, there can be some component coming from the following wave. So therefore you have to be careful about this algebraic process of going to negative frequency, positive frequency, etc. But it is pure algebra. So that calculation you may do, you write a program, you have not bothered, you suddenly find that something has become infinity, the program stopped because some number has become 0 here, that s omega by theta. So all I am saying that you have to be more careful, that is all. There is nothing difficult in concept, because yesterday we talked about following waves. In a following wave the transformation becomes very different. Sometime the wave the transform spectrum ordinate may become infinity. That such situation may occur when you do 3-dimensional spectrum. So one should be sort of careful about that. All right. So this is about the short crested wave. Okay. Now I want to change the topic now a little bit on what I mentioned before as what we call coupled motions. And then of course I want to talk a little bit about so-called natural periods, which is important because I will come to that about natural period. What it meant by coupled motion, that see when I did RAO, see we have written this, I will just tell in a very simple way. We have written a equation of m plus added mass into say heap this thing plus b heap plus c this thing equal to fz, like that we wrote, if you recall, and amplitude maybe this is fzt, like that we wrote. This was an equation we wrote when ship is only heaving, but in reality what would happen is that when it heaves, supposing you take a ship which is heaving.
We got with the single z.
Oh sorry, yes, you are very right, yes, single dot velocity, yes, very correct. Damping. Yeah, this is a heap velocity. This is what we call single degree of freedom equation.
Yes.
Okay. What I want to mention is that in reality though, what you would have done that in your vibration course most likely. Okay, it's very famous thing. But what happened in our ship motion is that sometime a motion in direction 1 will induce a force in another direction. Give an example. Suppose you take this body here. Now you are trying to pitching. As you pitch here, you see there is a pressure field created, and that net pitching may give rise to net heave force. This is exactly what happens to in the hydrostatic trim and parallel sinkage. If I put a weight here, what happens? It undergoes trim, but it undergoes also parallel sinkage. In other words, if I wanted to trim it, I will find out that the trim will necessarily cause a parallel sinkage. As you have seen that, because when the ship trims about LCF. So there is if you just trim the body, its mean draft has changed. Okay. This means that when I want to trim it, just pure trimming is not possible, unless of course LCF is just at the midship. So if you trim it, it necessarily may induce heave. So moment you try to trim it, there is a trimming moment, but there is also a vertical force, and that vertical force will cause the ship to have vertical velocity. So in short, to be very correct, you have to assume that all motions have influence on all other motions, and that is done by taking what is called coupled equation of motion. Then in that case, without sort of writing in detail, I want to say that what happens is that this equation of motion becomes more complicated, and this m plus a becomes a matrix now. It becomes mass plus added mass matrix into here the response. Let me write general response as x vector dot dot plus this will become b vector into x vector dot plus c into x vector equal to f vector. What happens is that it becomes complicated, more complicated. I will just explain that to you in terms of two so-called coupled heave and pitch. What is the coupling between heave and pitch? Actually, we can expand that more. I will just write that in a minute. So it becomes something like this. In fact, one people can write, if I call this to be A, it can be written as Aij into xj plus if I call this to be Bij into xj dot dot xj dot plus Cij into xj equal to Fi. Like that one can write, because you see this will be 6 by 6 matrix, m plus a1, it's a matrix, 6 by 6 matrix. This is a 6 by 6 matrix, this is a 6 by 6 matrix. Obviously you can write them as a11 x1 dot plus a12 x2 dot plus a13 x2 dot etc etc. You probably know that, okay? Right, you probably know that. So what I mean is that if you look at this, let us look at this coupled heave and pitch only and how it looks like. Now heave is actually, we are calling this axis system. This is 1, this is this is 2, this is 3, this is 4, this is 5, this is 6. So index wise, heave is 3 is heave, 5 is pitch. You know the motion, if I call x1, see, it is a convenient thing to write actually in an index form, x, y, z, and moment about x, y, z. You can call it x1, x2, x3, and rotation about x1, x2, x3 as x5, x6, x7, x4, 5, 6 axis. So index wise, if x1 is my surge, x2 is my sway, like that. So coupled heave and pitch maybe then 3 and 5. So in this equation will look something like this. See, if I just assume that there is coupling, heave induces pitch, then I will have I equal to 3 and 5, j equal to 3 and 5. These two will actually exist. So I will have a3 3 x3 dot dot plus a3 5 x5 dot dot plus b3 3 x3 dot plus b3 5 x3 dot plus c3 3 x3 plus c3 5 x3 equal to f3, and here a this is I is 3 3 3 5 and 5 3 x3 dot plus a 5 5 x, this is not 3 dot, this is 5, no sorry 3 dot, this is let me see this matrix, this 3 we have this matrix here, 3 and 5, 5 and okay, 3 only. This is, I think I am making a mistake here. This will be 5 here. This is 3. This is 5 dot dot plus b 5 3 x 3 dot plus b 5 5 x 5 dot plus c 5 3 x 3 dot plus c 5 5 x 5. Oh, sorry, not dot is not there. Like that, okay. Let me just write this and explain what it is. See, let me just take one case. Let me take this case. This is my coupled, the heave motion. This, there will be two equations, of course, coupled heave and pitch. What is happening? This is my heave exciting force, that is force coming in direction 1, okay. I mean heave direction 3, okay. Force coming in heave direction. Now this will produce obviously an added mass force for heave, and what is called here coupled added mass force for pitch. What does it mean? It means that even though I have given a heave, see, supposing I had a pitch motion x5, supposing I explained that, supposing I pitched it, I give an x5 motion, that x5 motion may give you a net force on the upward direction. See, I have to add all the force in upward direction. So this, of course, this is a force in upward direction. Now pitch can also induce a force in upward direction. Similarly, pitch velocity can induce a force in upward direction, like that. So what is happening is that we are adding now a coupling, that although the ship is heaving and pitching together. So now supposing it is heaving and pitching same time, what is my force in the z direction? There will be force coming because of heave, but there can be force in z direction because of pitch also. This is what is called couple. Therefore, you cannot solve heave by itself. You have to solve heave and pitch together, because heave is influencing pitch, pitch is influencing heave. This is what is called coupled motion. You see, what I wrote beforehand is a general one, where you are assuming without knowing that every motion is coupled with every other motion. We will find out that for ship, because it is symmetric about like center plane, heave, pitch and roll are coupled, and surge, sway and yaw are coupled, like that, because heave and pitch are always coupled with roll also, because see, when you give a heave it gets pitched also, and when you give a heave it can also roll, because you see, when you like this, when you try to heave it or when you roll it, it will cause a heave. So roll, heave and pitch gets coupled actually. But that's okay. I mean, okay, let me give this example a little bit in a different form. Supposing I have this shape here like this, okay. Now this is my motion here. This is my surge motion here. Now if I push here this side, whatever way, it does not give any force this side. So surge actually what is happening is that I should say this way: heave, pitch and surge, they get coupled. Why? Because if I give if I heave it or pitch it, especially if I heave it, it can cause pitch. If I pitch it, it can cause surge, because the forward aft is not symmetric. But if I surge it, it will not cause this side. If I surge means supposing the body is symmetric. So if I move it this way, that way, will it cause any force this side? No, because it is exactly symmetric both sides. Whatever I do, suppose the fluid gets pushed, equivalent fluid gets pushed here. So the net force in the y direction because of x direction motion is 0. This is called that having no coupling between sway and surge. In other words, there will not be a surge motion induced because you have given a sway, or vice versa. But that is a special case for a shape which is symmetry. That we need not worry. But what I am trying to say is that in general you will have, when you say of coupled motion, you need to actually have all this together, assuming everything is depending on everything else. But in a shape it turns out that is not always true. You can break it down to three parts. But you cannot have only heave. Heave and pitch and surge. Surge is not normally common. So this is the most common thing. Heave and pitch is the most common coupling that is always taken, and this is very important. Therefore, you cannot solve a problem usually only heave, but you have to have heave and pitch together. Because you see, to say the ship is heaving by 10 meter only, in reality actually if you oscillate by 10 meter, it will also have some kind of pitch motion. This is what is called by coupled motion. Okay, that is what sort of we need to know. Now, having said the coupled motion, I want to just very briefly tell. So, in other words, therefore, when you want to solve this equation of motion, you have to end up actually solving this equation, not one. See, earlier we said that you find out this, you find out this, you find out this, you can solve it, single degree of freedom. But in reality, you have to actually find all this, which is got 36 elements, 6 by 6. This is like it's a big matrix. This full thing will be a 6 set of equations, coupled equation with number of coefficients. So you find out all the added masses, all the dampings, all the restoring forces, then you get this. This is how it is. Okay, this is just for the sake of telling for completion. Especially as I said, heap pitch is important. I just want to briefly mention a very important thing in another few minutes time is with respect to this natural period. Okay, because this natural period has a very large influence on my response of the ship. Now, this is something I want to tell little bit. What is natural period? If you know this, if you draw an RAO with omega, there is a place where it goes like that. This is my natural period, You know that there is a high one, and this is important because if my spectrum is falling here, I mentioned yesterday, then I have got a very large wave. What is natural period? Means the ship is going to have a very bad motion in a single wave if that wave is of that frequency. Supposing a ship has a natural heap period of 10 seconds, then if the encounter period of that wave is 10 seconds, then it is going to very badly heap. So, supposing a spectrum has a large number of waves of 10-second period, then it is going to heap very badly. So, what is natural period? See, the formula for that is given by, see, if you go by this equation, actually what is called this equal to 0, it is formed from the omega natural is given by root over of c by m plus a, or T natural is 2 pi by omega natural equal to 2 pi root over of m plus a by c. I mentioned that, but why I want to say that is because I want to right now discuss little bit about the natural periods values approximately. Now, for heave, values for typically roll, heave and pitch. Remember that there is no C, restoring force in unrestrained motion of sway, surge and yaw. Why? If you push a ship, it says that nothing is bringing it back. If you shift it on y direction, it just stays there. It's like a car, it just moved there, nothing is holding it back. Only in a heave, roll and pitch, if you push it down, it gets pushed up. If you tilt it by an angle theta 10 degree, it will come back. If you pitch it by 2 degree, it will come back because the fluid hydrostatic will put it back. Now, for heave, the C is given by rho into G into AWP. Okay, and this is m plus a, mass plus added mass. Okay. Now, for roll, C actually roll, this formula will become for roll, this m plus a will become replaced by Ixx plus a, because moment it is now rigid body moment of inertia. So, this will roll T roll 2 pi of Ixx plus delta Ixx. What is Ixx? Ixx is basically nothing but about the x axis the mass moment of inertia, okay, divided by, now this C here becomes rho G V into GMT. This is the formula for that. It becomes rho G, actually it gives weight into GMT, because weight into ZZ is a restoring force. ZZ is GMT into theta. Therefore, it becomes C, weight into GMT. That's what it becomes. Now, this is how it is here, and T of pitch will be 2 pi of Iyy plus Diyy plus rho G into GML. Now, if you look at that, I just want to say here very, very briefly, we may not have much time. See, this has become 2 pi of the rho G into V is the mass into 1 plus the added mass coefficient divided by rho G into, rho into G into AWP. You see, look at these formulas. Heave natural period becomes something like this. Now, yesterday I mentioned that if you can calculate, and we will do that in our assignment, that if you have AWP high, okay, compared to delta, then this becomes small, and in fact for a typical barge it becomes 6 to 8 seconds, for a ship maybe 12 to 14 seconds, for a semi-submersible much more. Okay, this is how it becomes, these numbers. We should have a feel about the numbers. In here you see T roll. If we can find out if GMT, it is inversely proportional to GMT. If GMT is low, T roll will be high. So you will find out that if I have a very stable ship, GMT is high. If I see, you want GMT to be high for high hydrostatic stability. You know, GM is high means very stable. But if GM is high, then T roll becomes low, and you can find out these values that the typical shape, this value will again come out to be for a very small shape with high GMT, maybe 8 to 10 seconds, but for a bigger ship maybe 12-14 seconds. It has been found that people are comfortable if this period is about 15 to 20 seconds, or maybe 15-16 seconds. But to do that, you have to actually have GMT to be equal to less. Now, there is this contradiction that comes. A passenger vessel, passengers will not ride your ship unless they are comfortable. Therefore, they want somewhat good T natural, 15, 16, 18 seconds. But it is a passenger ship, you have got a higher requirement for GMT, because it should be more safe. So there is a contradiction that a designer has to figure out. But a ship with a GMT high is known as a stiff ship. With GMT low will be called a soft ship. A stiff ship is more stable. So you have to be a compromise. But we will not work it out, but you can work it out from this typical number of values, because it is easy to estimate. dIxx is very small. Ixx is mass into moment of inertia. Mass is given by the displacement. Moment of inertia about x-axis will be something like about 30% of breadth. Because you see, if you take a ship here, and if you take a moment of inertia about this line, this is my B here. See, all the hulls are on the side. If you can approximate, it can be between 25 to 30% of the breadth, because you see, like this, the moment of inertia will lie somewhere here, approximately this kind of distance. If you rotate that, it is between a solid cylinder and a hollow cylinder. You can make it out, because obviously the more weights are there on the shell, more side frames are there. Okay, so it is more like a hollow cylinder, shifting a little outside, but not fully hollow cylinder, because quite some weights are also scattered inside. So it is in between that, and people find out that it is about 30-35% of breadth. See, if it is exactly half, it will be 25%, because the breadth is full thing. Remember, this is my B. So if it is halfway of B, it will be 25%. It is little more than that. So you can estimate that. You know the GMT value. GMT may be, our requirements is only 0.15 meter, but most ships have 1 meter or so. So you can find out what is T roll, and you will find out that this comes out to be around 10 seconds. Similarly, you can find out this also. This also actually becomes of similar order, because you see GML is high, but IYY is also equally high. So they get cancelled in same order. Why I mention that? Because it turns out that for a typical shape, all natural periods happen to be somewhere between 8 to 16 seconds widely. Okay, let us say 8 to 16 seconds. Now you take a small C state and a large C state. This may be about 8 seconds, this may be about say 16 seconds. And what I mean is that very small C state to very high C state, the peak is between 8 to 16, and it turns out that my natural periods are also within that range. You see, it is not that it is very for a typical shape. For a semi-submersible, it is outside. For a semi-submersible, it comes, see, my umbrella comes here. But for a ship, it comes, unfortunately, all the peaks come actually in between somewhere. So therefore, what is happening is that ships do undergo large motions in the typical, what we call everyday weather that you meet.
16 to 8 within that.
More or less. See, 8 seconds will be about 100 meter long wave, or maybe 6 seconds it can be. Actually, it can be even lower to 6 seconds at a very small sea state. Like 6 seconds means maybe 80 meter long wave. This is why, now again, as I mentioned yesterday, smaller boats and stiffer boats, suppose the ship is stiff, will have a roll and all on this side. So if you take a barge with a high GM, okay, then it has got a low natural roll period, and even in the smallest wave it is going to have a very large roll. So it is not comfortable. So this tuning is very important in any motion, and that's why I mentioned this, because it turns out, unfortunately for ship, that the natural periods are not widely far from the kind of peak period of the waves that occur. See, had it been, I'll finish in a second, if you take a ship of 100 meter long wave, you know that ship would behave badly between maybe 3/4 of the length to twice the length, between 75 meter to 200 meter long waves. And it turns out that the waves that occur in the ocean are of that order. They are not 1 kilometer so many, they are not 20 meters so many, they are mostly 150 meter. So you see that this factor, therefore you have to have in the design tuning. This is why this sea keeping is becoming more and more important with time, because you don't want a bad ship with respect to sea keeping. Anyhow, so this is about this natural period. We'll talk little more later on, and I'll end it for this lecture now here.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape, and IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.